Hello everybody. In the previous video, we started a transient response analysis for dynamical systems and we technically analyzed simple first order systems. Now we will move on to second order systems, which is technically more interesting. We will have different kind of cases, and I can clearly say that majority of the physical systems that you will control in physical life, in real life, is either first order or second order. Technically, these two systems covers important characteristics of systems that are physically available in real life. Okay, so we have electrical system, we have mechanical system, and we have a rotation mechanical system. This is an RLC circuit, this is spring damper, translational, and this is a rotational spring damper. Okay, if we model these systems, we will see that all of them can be modeled in this general form. G of S is equal to some constant, we can call it a DC gain or something else, omega n square S square plus 2 zeta omega n S plus omega n square. Okay, so which means that numerator dynamics is constant, okay, for this type of systems, and denominator is a second order system, and instead of writing these coefficients separately, we can write this in this form. Okay, so the importance of this form is that omega n is called natural frequency of the system. Natural frequency of the system, okay, and psi or zeta is called damping ratio. Okay, that's great. So of course, for physical systems with passive elements, we know that omega n is greater than 0. It's also greater than 0, not equal to 0, and psi is also greater than 0, and KDEC is just a gain which can change from the system and system like significantly, but this part is the part that we will try to analyze in this lecture. Okay, that's great. So under what conditions we obtain different behaviors, and it is directly related with the structure of this transfer function and characteristic equation. Okay, let's clean this and let's analyze this. Okay, that's great. Okay, that's great. So we have a characteristic equation. So let's compute the poles of the system. Under the standard form, the poles can be written as this. S12 is equal to psi omega n plus minus omega n psi square minus 1. Okay, so these are the solution of the roots or poles of the system. Okay, and depending on the value of psi, okay, so we can have different structural responses, different kind of behaviors based on these pole locations, and it depends on the psi. Okay, let's start with the simplest case. Okay, case 1 when psi is equal to 0. Okay, which means that there is no damping in the system. Okay, it generally happens when there is no damping, friction, or resist in the system, which is kind of fictitious, I can say that, or like imaginary system. Okay, because there's always some sort of damping, we know that. But we can technically achieve this using active elements. But this is basically, it means that there is no damping of the system, and it is also called undamped dynamical or second order system. That's great. So in this case, G of S is equal to omega n square divided by S square plus omega n square. Okay, so as you can see, we have two imaginary roots. So S12 is equal to plus minus J omega. Okay, once we have imaginary root, if you remember your Laplace transform knowledge, we should obtain a sinusoid or cosine like signals at the output. Okay, so let's try to look at the step response of the system, which is technical step response is the most important type of input that we will analyze in this course. Y of S is equal to, since it's a step response, is equal to 1 over S, it's the input, times 1 over, okay, that's about 1, okay, omega n square, S square plus omega n square. Okay, so we need to do partial fraction expansion. It is equal to 1 over S minus S divided by S square plus omega n square. Okay, So if we take the inverse Laplace transform, we will see that this is equal to 1 minus, and if you remember, this is a pure cosine signal, cosine omega n times t, of course, for t is greater than or equal to 0. So it is a pure oscillator signal. There's a constant. Okay, so let's draw it quickly and try to understand the behavior. Okay, so at t is equal to 0, as you can see, it starts from 0. Okay, that's great. That's great. Okay, so and we know that the maximum minimum is in between 1 and -1, so it will have a response like this. Okay, that's great. Okay, so I have a much nicer figure. So maximum happens at 2, minimum happens at 2, average, or let's say response, is obtained at equal to 1. Okay, so this is critical. Okay, so it's equal to 1. So this is an open loop system, but we can technically adjust it to make it look like a closed loop system. And what we call this part is overshoot. Okay, so this is kind of meaningless for the system, like talking about overshoot. Okay, so what's the overshoot? And once we go to different kind of systems, you will understand the meaning of overshoot is better. Okay, so what is the frequency of oscillations? Obviously, it's equal to omega n. So this system oscillates at the frequency of natural frequency. Okay, since there is no damping in the system. This is the basic idea. Okay, that's great. So if you look at this system from the perspective of stability, if you remember, I apply a bounded input to the system. It is bounded output. So you may assume that it is bipolar stable, but it's not. Okay, because I apply a constant, it oscillates. So instead of applying a step input, if I apply an input at the frequency of the natural frequency, I know that I will obtain a bit different behavior, and instead of cosine t, I will have t times cosine t, and it will blow to infinite. It will be bipolar unstable. We will talk about the stability later, but I want to give some intuition even at the phase of transient analysis. Okay, good. So this is undamped behavior. Okay, it's called undamped behavior. As you can see, if we apply a step input which is constant, it oscillates at the output. Oscillation frequency is equal to natural frequency. Okay, that's great. So let's move on to the case 2. Okay, when psi, it's also a special case, is equal to 1. Okay, so we call this system as critically damped. Okay, so unlike undamped case, this is a desirable, a good case. I will tell you before just even drawing the response or finding the response. Okay, so this is a desired behavior. Okay, you can think as a design criteria, an optimal case or something like that. Okay, so let's analyze it quickly. G of s is equal to omega n square divided by s square plus 2 omega n, because psi is equal to 1, plus omega n square. If I obtain that, it is equal to omega n square divided by, this should be square, sorry for that. Okay, divided by s plus omega n square. So I have a repeated root, as you can see. So if I apply a partial, no, I'll not apply partial fraction for this. Our goal is again finding a step response of the system. Okay, so y of s is equal to 1 over s times omega n square divided by s plus omega n square. Okay, if I apply the partial fraction expansion, I know that since I have repeated root, it will look like this: minus 1 over s plus omega m plus omega n square divided by s plus omega n square. Okay, that's great. Okay, so we computed the partial fraction expansion. Now we can find the step response by taking the inverse Laplace of the expression. Y of t is equal to 1, because it's step, minus, it's a single root, it's equal to e to the power minus omega n t. Okay, so minus, this is like double roots. Once we have repeated root, if you remember, it should be equal to t times omega n times e to the power minus omega n t. Okay, that's great. So we computed the response. As you can see, it looks like this. Okay, so let's analyze this a little bit. Okay, before drawing the response, we can also draw the response. Don't, it's not a big deal. So if we plot the pole zero map, we know that there are two roots. Okay, here. Okay, it's a repeated root and it is equal to minus omega n. Okay, as you can see, S1, 2 is equal to minus omega n. It is constant and it is real. Okay, that's great. And if I plot the response, okay, it will look like this. Okay, that's great. So let's change the color. And the steady state value is equal to 1. Okay, so this is the critical damp case. Okay, so this is 1, it's constant. Okay, and we know that as time goes to infinity, this will go to 0, this will go to 0. Okay, so this is going to 0 and this is also going to 0. So if we ask which one goes faster, okay, so because of this t, okay, it will speed up the technically convergence speed. So after some time, let's say t is like larger than 1 or some setting time or time constant. Okay, if t is larger than the time constant of the system, okay, and time constant is equal to 1 over omega n, it will be approximately equal to this, okay, because this will go to 0 faster, so this part will dominate the behavior. Okay, from this perspective, you can understand that a critical damp system acts like a first order system. Okay, this, and believe it or not, it's a good thing. The second pole is going to the 0 faster than the first pole. It becomes a approximate the first order system. If you, for example, perform a system identification or some sort of analysis, you may even assume that the system is a first order system, okay, because it's very close. The double root case or critical damp case acts like a first order, especially after t passes the time constant of the system. Okay, so this is the basic idea. As you can see, it is equal to 1. Okay, that's nice. Now we will move on to more general or more, let's say, probable cases, because psi is equal to 0 was undamped, and psi is equal to 1 is equal to critical damp. These are specific cases, and this happens only when psi is equal to a specific value. Okay, now let's analyze the case when psi, okay, let's change the color, zeta or psi is greater than 1. We have an overdamped case. Then what's overdamped? The damping, or like say the friction, the resistance, or I don't know, the dissipative effect is too much. It's exactly like this. It's overdamped. It means that the damping level is higher than the critically damped case, and we will now understand what does it mean. Okay, so in this case, if I draw the poles, or if I compute the poles of the system, P1, I have 2 poles, P2 is equal to this, psi omega n plus omega n, okay, psi square minus 1, it is equal to psi omega n plus, not plus, okay, this is minus omega n, okay, this is psi square minus 1. Since psi is larger than 1, okay, both of them are positive. Okay, so one important thing is, if you look at P1 and P2, you will understand that the first pole is greater than minus omega n, and the second pole is less than minus omega n. So what does it mean? Let's draw the pole zero plot. Okay, so we have a pole here. Okay, this is P1. We have a pole here. This is P2, and omega n is right here. This is minus omega n. Okay, so if I keep omega n, or my natural frequency fixed, if I only change the damping, what I do is I put a pole to its left and I put a pole to its right, and it really have a fundamental limitation on the transient behavior, or limiting case or constraint. Okay, so why? So let's find the output and try to better understand the response. Okay, so if we compute g of s, or if we rewrite g of s in terms of p1 and p2, you will see that it will be equal to p1 times p2 divided by s plus p1, s plus p2. Okay, that's great. If you compute y of s, it will be equal to 1 over s times this quantity. We will apply partial fraction expansion. Y of t will be equal to 1 plus p1 minus p2. The constants are not very important. You can just ignore them. p1t plus, not plus, okay, oh, not, it's no problem, minus p1 divided by p1 minus p2 e to the power p2. Okay, that's great. So as you can see, we have a constant. Okay, so let's draw the output. We have a constant, and constant is equal to 1. We know that both p1 and p2 are on the open left of plane, so they're negative. So negative exponential means that they're decaying exponentials. So I know that as time goes to infinity, I will go to 1. Okay, so it will look like this. Okay, so as you can see, it is very typical or similar to the critical damp case, right? Okay, so that's nice. Now the question is, how fast it will go, or which part will dominate the behavior? Okay, so the basic idea is the fast part. So if I look at this, because this is constant, I have 1 and 2. The fast one will go to 0 quickly, okay, or with respect to the other one, and the behavior will be dominated with the slow pole. So which is slower? Of course, P1 is slower, okay, because e to the power, for example, minus 100t or e to the power minus 1t, of course, this will go to the 0 very quickly, okay, compared to this. So if I have like a two-pole system, which is minus 1 or minus 100, of course, this will be dominated by the slowest pole. Okay, and again, the second order system, as time like is, let's say the time is larger than the slowest time constant, okay, the slowest pole will dominate the behavior, and it will again act like a first order system. Okay, but different from the critical damp case. Okay, in the critical damp case, if you remember, let's change the color. Okay, I have double pole here. Okay, the slowest expression is this, e to the power minus omega n t. In this case, this is critical damp case, and this is overdamp case. We have e to the power p1t. But as you can see, since p1 is closer to the origin, it is slower. So it means that the limiting case for overdamped systems in terms of convergence speed is the critical damp case. Okay, so okay, if I draw the critical damp case here, let's say that it is like this. Okay, if this is psi is equal to 1, if I improve, or if I increase, not improve, of course it's not improving, my psi or damping ratio, I will move in this direction. Okay, it will be like this. So in this direction, okay, in this direction, psi is increasing. Okay, so what does it mean? If I am in overdamped region, including the critical damp case, if you increase your damping ratio, it means that you will slow down your system. So it's kind of a bad thing, right? So technically, control systems, we want to reach the steady state value as fast as possible if we don't have limitations on the input and other kind of constraints. So this is a desirable thing to go to 0 faster. It is technically a measure of relative stability. If you go to 0 faster, or your steady state value faster, it means that you are more stable, you are faster, and you are technically a better system. So if it's possible, if you can do it by controller or by this Z-dynamic system, you shouldn't pick psi very large. Okay, technically you should pick the damping ratio close to the critical damp case. Okay, so you may not achieve this exact ratio because it's a like specific number. There will be some noises and some untransformed system, but being close to the critical damp case is a good design criteria for control systems. Okay, good. That's nice. Now we will move on to the third case. Okay, case 3. Case 3, where psi is less than 1, larger than 0, which is called underdamped system. Okay, so underdamped. So what this must be underdamped? Let's just look at the angle. Underdamped means that the damping level of friction, level of the resistance or dissipation is not enough, okay, compared to the critical damp case. And we will see what does it mean in a second. Okay, so in this case, if I compute the poles P1, 2, I will obtain that minus zeta omega n plus minus. Okay, so I will write it like this first, omega n psi square minus 1. Okay, psi is less than 1, its square is less than 1, so this is technically negative. Square root of a negative is a complex number, so what I do that instead, it's equal to minus j omega n 1 minus psi square. So what I have a complex conjugate entity. Okay, this is important. Okay, so this part, let's call it sigma, and we call this part omega d. Okay, so since omega is in the unit of frequency, omega d also has a unit of frequency. Okay, we call it damped natural frequency or damped resonant frequency. Okay, so one important fact about this case is, if I take the magnitude of this complex quantity, so if I take the magnitude of poles, I will see that this is equal to omega n. Okay, that's nice, as you can see. So we are just reaching somewhere. Okay, so if I plot the pole zero plot before going into the step response, okay, we will plot the step response. But if I plot the pole zero plot, which is, I think, more important than just finding the response, I will see that. Okay, since omega n is constant, it's the magnitude. Okay, these poles are distributed on the circle, okay, which has a radius of omega n. And they are complex conjugate. Of course, they have the complex conjugate. Poles are located, if one is located here, the other one is located here. Okay, that's great. So the real part, we know that it's equal to sigma or minus sigma. It's okay, no, it's minus sigma xk, exactly, or it is equal to minus psi omega n. Okay, it's the real part, it's the exponential part, okay, which is not oscillatory. And the complex conjugate part, this part is equal to j times omega d, or it's equal to omega n times 1 square minus psi square. And this angle, which is very important, is called, okay, let's change it again, is called phi. Okay, this angle is equal to phi, which is the technical angle between the imaginary part and the real part. And this monotonically related, depends on the damping ratio of the system. Okay, so let's analyze it a little bit. What happens if I drop damping? Okay, so if damping is equal to 0, I know that I'm a critical damp system. So damping 0 means that my system is located here. No, sorry for that. Okay, sorry, it's wrong. Okay, that's great. Okay, sorry for the mistake. Okay, so if there is no damping, if you remember, I have two purely complex conjugate entities, and purely complex. Okay, and one pole will be here and other pole will be here. If my damping is equal to 1, my poles will be repeated real poles, they will be here. So technically, in this direction, and in this direction, psi is increasing. Okay, that's great. So this is technically everything that you need to know at this point. Now let's try to find the response of the system. Okay, so if we write the response, okay, as you can see, since we have two complex conjugate roots and we have a constant, okay, at input, because it's a step input. If we find the general solution, okay, y of t will look like this. Okay, some constant plus c1 e to the power minus sigma t times cosine omega dt plus c2 e to power minus sigma t, if you remember from your differential equation knowledge, sine omega dt. Okay, so and then what we do is we first compute for the particular solution. Okay, that's nice. And then we use the initial conditions, and we know that initial conditions are 0 because we assume that initial conditions are 0, and we compute c1 and c2, and then write the whole solution. So the whole solution will look like this. I really recommend you to go over the solution by yourself. Okay, e to the power minus sigma t, okay, cosine omega dt plus, okay, this is psi 1 minus cosine square root, okay, sine omega dt. That's great. You can also solve this using Laplace transform. You can use Opta or MATLAB to also find the time domain analytic expression if you use the symbol map toolbox. Okay, that's nice. But instead of using this expression, we use like magnitude and phase notation, and we write everything in the sine form. So y of t is equal to, okay, that's great, 1 minus, okay, a constant, and constant is equal to 1, okay, 1 minus psi square, okay, e to the power minus zeta omega n t, okay, sine omega dt plus phi, and of course t is greater than or equal to 0. Okay, so how we compute phi? It's very easy. Tangent phi is equal to 1 minus psi square divided by psi. This is in square root. Okay, so we can compute tangent phi, and we know that sigma is equal to e to power minus psi omega n. Okay, so what is this? It's under damped. So let's draw the response to better understand what does it mean being under damped. Okay, so let's draw this. Okay, that's nice. So if my response in this form, in standard form, okay, if my psi is under damped, so it means 0 and 1, but not equal to 0 and 1, my response will be exactly like this. So this is the steady state value, equal 1. And if I draw the response, it will look like this. Whoops. Okay. That's nice. It goes like this. So this is the response when psi is less than 1. Okay, so this is the whole idea. And now let's try to analyze and understand what happens if I play with some parameters. Okay, that's nice. Okay, so I'm keeping omega m constant. Okay, I'm just changing psi. Okay, first of all, when psi equal to 0, it is underdamped, and I know that underdamped or the undamped case is equal to, it look like this. Okay, whoop, and its frequency of oscillation is larger. Okay, so it's look like this. Okay, so I'm just doing randomly. Okay, it's a pure oscillation. Okay, if psi is equal to 1, there is no oscillation. It looks like this. So in between, I have a behavior which is oscillatory, but it's decaying oscillations. The amount of oscillations are decaying. So at t goes to infinity, it is reaching our steady state value, which is nice. But in between, I observe some sort of oscillations. I really don't want these oscillations, or I want these oscillations to be as small as possible. This part is overshoot. I will talk about in the next lecture. Okay, it's called overshoot. We will try to minimize that. We will try to minimize other or like adjust other performance metrics. I will talk about later, but the idea is these oscillations are generally, for majority of the systems, are unwanted. There could be small oscillation which can be acceptable. Okay, if the frequency is large, if the amplitude is small, that's nice. But these oscillations are not required because it's really bad thing. So it is assumed that we are trying to control the speed of a car, and we want to go like 60 kilometers per second, but when going that, I have oscillation, and my speed changes like in a sinusoidal fashion in between plus and minus 5 kilometers per hour around some equilibrium or desired point. This is really not a desired response, and obtaining overdamped let's say underdamped behavior, oscillator behavior in control systems is very possible if you don't adjust your controller and your system nicely, because it's related with the amount of damping of the system, which means that the level of damping or energy dissipation is not enough if you obtain this kind of behavior. Okay, so that's nice. So we know that. So we know that if I change the damping, if I increase the damping, because from 0 to 1, I will approach the critical damp case, so it will have a good effect, and I know that I will decrease this overshoot. Okay, that's nice. So let's look at the omega d. Okay, so if I increase damping, okay, I know that I will approach the real axis. It means that I will decrease this angle or the imaginary part. So omega d, the frequency is decreasing. Okay, and at some point the frequencies will basically disappear if I perfectly equal to 1. Okay, so it's one of the things, frequencies are decreasing. And other important thing is, as you can see, if I increase my damping, I will move in this direction, my real part will deviate from the imaginary axis, which means that it will have a faster response because of this effect. So it will approach to t is equal to or its steady value in a faster fashion. Okay, so increasing damping if you are in the underdamped region is a good thing. So what's happening if I increase damping? I'm approaching to the critical damp case. Similar to the overdamped case, if I decrease my damping, I approach the critical damp case. Okay, so the basic idea, the best response in a second order system is the critical damp case. Okay, so if you cannot achieve this exactly, what you do is you try to manage such that you are at least close to this critical damp case. You can be a little bit overdamped or a little bit underdamped. It will be still okay. You may have some oscillations, you may lose some speed, but it will be still close to the optimal response.